Our next speaker has come all the way across town from Sandia National Labs, and great to have. One of the things we really want to do is encourage more interaction with the National Labs. We are co-founding a New Mexico AI consortium that includes all the universities and the labs, and where this is one example of trying to build up some partnerships. So I will turn it over to John Slightam. Thank you.
Thank you, Melanie. Can you hear me on this? Is this working? Oh, no, that works. Okay. Thank you, Melanie. So today I want to give a talk on data-driven and AI approaches for robotic manipulation, but the context of this is really how this impacts the future of work in the age of robotics and AI, and how this is changing how we do work in the DOE complex. So I'm going to talk about 3 different problems we've solved using data-driven and AI approaches for robotic manipulation. I'm going to start with talking about embedded semantics for inferred model constraints. And that really motivates the following problem we've solved, which is going into constrained object motion estimation using physics-informed neural networks. And this starts to allow us to operate in more so the real world where things are truly unstructured. And then I'm going to finish off by talking about control parameter inference and how these things tie together to really realize kind of more true autonomous manipulation, which is motivated by like how we interact with the world. And this large effort is notionally going towards answering the following question, which is how can we bridge the gap between perception and successfully acting on the world? So how do we learn physics of how things move in space using AI methods so we can successfully start interacting with things and not just be more or less an autocomplete with a large language model or some of these other techniques, but how can we start physically doing things that are meaningful? So in answering that, we want to share a philosophy on using AI for pragmatic problems with robot manipulation and see how we can leverage these approaches to transform the future of work in the DOE complex, which a lot of the work is dirty and dangerous, so we want to keep humans out of harm's way notionally. So we'll discuss that towards the end, how we can apply some of this work. So first I'm going to talk about this work we've done on embedding semantics for inferred model constraints. So some of our prior work showed that we can successfully embed semantic information into convolutional neural networks such as YOLO and its various versions. Let's see if this video will play. Well, I don't know if that video is going to play, but it is a video of basically we can see the different labels of the types of the door, and you can see what type of door it is with some semantic information. So it's actually an interior door with the handle on the left-hand side and what type of handle it is and whether or not you need to push it or pull it. And from there, we can actually infer a model from that. And so we're able to explicitly classify these different types of doors and subsequently use that information downstream for door opening, as shown in the sequence of images on the bottom right. And notionally from that embedded semantic information, now the video is playing. So you can see, it's internal pull door handle, which is on the left. From there, we can infer this kinematic model. From that, we can actually then create a baseline path plan, engineered control parameters, and also coordinated base arm motion if that's needed for whatever type of door that we see. So we realized this in an autonomy stack for autonomous door opening, where it takes in the classification of the object of the type of door. Once initiated, it passes that information, creates a waypoint in front of the door. That robot then traverses to the waypoint target, changes control mode, and then goes to a different viewpoint to see where the handle is, and then subsequent waypoints are determined on the fly with a localization algorithm. And then the arm continues to execute that kind of base motion plan for the type of door that we observed, and we're able to then successfully open the door. After it's completed opening, arm goes into the stow position, and then the base of the robot actually proceeds to traverse through the doorway and continue doing the task we want to do in terms of our overall mission. What really makes this successful is two things. It's the classification for manipulation, so embedding that semantic information that we can use to create models to help ensure success for manipulation problems, and also the arm control, which can also then be inferred. So we've had quite a bit of success with this. The video on the left here shows some different type of door opening. This is that same interior door, but on the other side. So we're actually at this viewpoint or perspective for the robot. It's a push door. Interesting enough, this requires kind of base and arm coordination because if you were to push that door all the way or its full sweep, the arm doesn't have sufficient reach. So we kind of start leveraging that coordinated motion. Now extending that further is we can start doing dynamic manipulation based on this exterior door that we see. We can leverage rapidly moving the base and the arm in coordination to transfer momentum to large heavy objects like this exterior door that has a door closer. It's a large door and we can successfully traverse into a building from its exterior. And this video going on shows that same door that we can do from the other side and exit that building. So we can have a robot autonomously traverse a space, make maps, open doors to enter a building, go into different rooms, which is, doors notionally for years have been showstoppers for physical robots just because they're largely unstructured and hard to manipulate in really a real world setting. And this one's quite progressive. It rams into the door to get it to open. But this work has really highlighted many challenges in transitioning to true unstructured environments. So how we operate in the real world. Everything can be variable. We see things we don't see every day, different types of doors. I sometimes make mistakes opening doors. So, real robots in the real world have very real challenges doing this. And this notionally has motivated some ongoing work where we try and use systems of neural networks working together to better learn models of the environment and how to interact with them in a more unstructured way. So this next problem we solved is on the constrained object motion estimation using physics-informed neural networks. So like I said, this problem space is we need to really enable more robust manipulation behaviors to unstructured environments. We have a test bed we're testing this kind of framework on, which is like this block and a slider system as an exemplar. So it's a really simplified, constrained motion problem. There's some bearings, a thing we want to move or push along. So how can we create these systems of systems to kind of manipulate and understand how things move? And the key to this is just understanding how objects and systems move. So our approach is kind of using those embedded semantics that we did before, localizing them in space, and then using physics-informed neural networks to create object model constraint estimation. So we can see where a bearing is with respect to a rod, that there's multiples of those, and where it is with respect to this block that we want to move in space. And then we can create a motion model that we can then act upon with our physical robot and do this in a more robust fashion. We started with this using an algebraic approach, but notionally the principle is that we have this lambda matrix that indicates like permissible motion in space. If it has a 0 in the diagonal, that indicates that one of the principal axes, where it's 0, you'll have some kind of body frame permissible motion that then you can use for creating a motion plan. So we started using an algebraic approach as with our first methods, and this video shows kind of the results of this, where it's like in real time we're able to create this lambda matrix, which we then use for creating a motion plan to push a block in a desired path that we want for the robot in an autonomous fashion and in free space. And we've extended this to using physics-informed neural networks, where we actually just feed in the different types of semantic information, where they are in space, and then outputs that lambda principal vector, which then we can use for creating a motion plan. But interesting enough, we get a lot better performance when we use like the norm of the basis of that unit vector in the loss function. So how does that compare to our algebraic approach? Well, this top plot shows basically the magnitude of the percent error of the algebraic approach versus the physics-informed neural network, which the algebraic approach really breaks down as you look at things at a large degree of angles with respect to where the robot is in space, while the algebraic approach notionally does do well in certain instances if you're looking at things like straight on in a perfect way, but the real world's not like that. So this physics-informed neural network demonstrates greater adaptability and scalability for kind of more diverse problem sets. And we've shown too recently that we're able to extend this to doors and other types of motion models within the same neural network, which that's really promising. And some of these bottom plots just indicate what the loss function errors are, the total loss compared to the mean square error for a traditional loss function with a deep neural network. So we are getting a much improved performance using that physics-informed aspect. So the final thing I want to talk about is control parameter inference using deep neural networks. So I showed the video on the left earlier, and notionally this arm is using a force feedback approach to make sure it doesn't break itself or the environment. And notionally engineered force feedback solutions aren't really that resilient to broadly coupled manipulation problems. So we did a lot of testing with that type of control for use in the real world. Notionally it works really stable. Then we were going to extend it to a different application where we're tugging on a rope we want to pull, and actually just with the system properties of that rope has a certain spring stiffness, and that dynamic interaction between that force feedback controller and that rope we're trying to pull pretty hard on actually causes some stability issues. So this is another problem that robots have when going about working in the real world. So we want to solve that. And one thing we did was kind of look at a space and create a data set of looking at passivity analysis between many different scenarios of environmental interactions that interact with our robot in the worst case scenario, as well as a stability analysis perspective. And we took all that data and created a deep neural network. This plot on the right is a simulated validation of the closed loop system response. So it notionally emulates making contact with the environment. Kind of that base scenario is the blue line, and that kind of shows this oscillatory behavior that we saw in the video of like rope pulling. But if we turn on that neural network adjusted damping parameter that we determined with all the analysis, we actually can dampen out that response and make it stable quite quickly too. And this is pretty promising for real-time applications because now we can have this general function approximator that maps this large scope of possibilities of things we might interact with, and using simulated data and be able to adapt to that really, really quickly, and I think more so or more quickly than adaptive control techniques. So we've more recently implemented this in hardware. So as soon as we turn this on, our system goes from this unstable oscillatory behavior and actually dampens out that response behavior to something that's desirable, where we don't want things shaking around. Some examples of this, it's some kind of door we're trying to pull open and hold open. If it has a closer, our robot might slip off the handle, or if we're trying to turn off a switch that's preloaded, that's a pretty hard thing to pull in like a disastrous response scenario. We don't want to slip off of that, and we want to execute our task. So this enables that type of behavior to be successful when interacting with the real world. So I presented 3 different things here today, like problems we've solved with kind of data-driven and physics-informed AI approaches for manipulation. Where the power is with this is we can solve really niche problem spaces with data-driven approaches and apply those to real-world problem spaces. More recently, we applied some of these techniques down at the waste isolation pilot plant down in Carlsbad, New Mexico, which is where a lot of radioactive waste is stored. They have these big bulkhead doors that need to have this rope pulled to open them. So we're able to apply these techniques to do this in a more autonomous fashion because these bulkhead doors are initially a showstopper for the robot traversing through the underground there. So this opens up many more opportunities for applications and robots handling radioactive waste. And this initially can also impact places like the Hanford site in Washington and help with dangerous tasks in the DOE enterprise. These images down in the bottom are initially at Hanford. This is what's called a pit. Basically, this is a highly radioactive environment, and a user that needs to connect hoses or decouple them for transferring radioactive waste to do some cleanup, they'll get their full dosage of radiation that's for the span of a year in a single day. So having a robot do this frees up staffing resources, keeps them out of harm's way. So just having the ability to couple and decouple hoses and do these actions, I think, is really where we're going to impact work more so with the DOE enterprise and national security as a whole. So with that, I want to thank you all for listening. I also want to acknowledge all my colleagues in our department, 6533. We have some interns here, like Calvin, who's contributed as well. A lot of talented folks, and thanks again, Melanie, for inviting me.
Okay.
Sure.
So you mentioned that. So if you use algebraic models, that is a linear model. So it's accurate, but probably only in a very limited region in the space, right?
It was like we had a trigonomic function in there as well.
Okay, I see.
But with that, you have a singularity, and we found with our deep neural network or the physics-informed deep neural network, we don't really have an issue with the singularity there.
Okay, but I have a question that have you tried to use multiple algebraic models for different regions in the space to improve the accuracy? Because when you have algebraic models, probably the whole closed-loop system is easy to be verified. But when you have deep neural networks, the verification might be difficult.
So you're saying, have we considered using multiples of the algebraic approaches?
Yes.
It's been a thought experiment.
Yeah.
So, but I think what we've shown already is that the deep neural network approach is able to handle like different mechanical problems
I see.
that otherwise we're going to have to again engineer. So I think it takes away like the engineering approach where like we have to we're trying to embed the human expertise in how the model's created with the physics-informed neural network, whereas we have to solve that algebraic problem up front.
Okay.
So it's a big time save in terms of like how we apply that in an autonomy stack for like robot manipulation on constrained systems.
Okay. Thank you. By the way, I have one more question. That is about uncertainty. So how about if your perception or you know that neural network might have some noise injected?
Yeah, so we that same model, the physics-informed network, actually works better with noise added to it. I don't remember the exact values of it, but having no noise in the synthetic data that we use actually performs worse than if we added some noise because of that. The reality, there's some uncertainty with the estimation of where things are in space. It moves around. Data with a robot that has noise. Everything has noise in the real world.
Yeah.
And these are very real problems. So like when we create synthetic data, we factor that in.
Yeah, I guess probably the noises in training probably helps to reduce the overfitting problem.
Yes.
Yeah, this is probably.
I think without the noise, you have the overfitting problem.
Yes.
And it just does not work well.
Yeah, thank you.
Yep. Any other questions?
Well,